Hello everyone, my name is Adnan Ajas and I lead the 5G program at the Bristol Research and Innovation Lab of Toshiba in the UK. Today I will be presenting our technology demonstration on open and programmable 5G network in a box and also its performance evaluation. To give you the background and motivation for this demo, I will very briefly explain some of the latest technology trends. I'll start with industrial IoT systems which focus on connecting industrial assets like machine and control systems and exist across a range of industrial domains including manufacturing, mining, and warehousing and logistics. Industrial IoT systems are mission critical in nature and require high performance connectivity to meet stringent performance requirements, especially in terms of latency, reliability, and data rates. On the other hand, 5G technology has been designed to provide very high data rates, ultra low latency, and at the same time supporting very high connection densities. Hence, 5G offers what I would like to call a unified wireless interface to support the diverse requirements of different industrial applications. The third trend is of private networks, which are crucial for unleashing the potential of 5G technology for industrial communication. Private networks offer various benefits including dedicated coverage and capacity, customized service, as well as intrinsic control. The fourth trend is of shared license spectrum, which is becoming available in different parts of the world due to various regulatory initiatives. This shared license spectrum empowers industrial stakeholders to run their own local 4G and 5G networks with dedicated equipment and settings. On the other hand, SDN and NFV technologies provide programmability, which is important in private networks from various perspectives, including fine-grained control and customization. And finally, a number of recent projects around 5G are adopting the open source model, which is promising for developing white box 5G solutions for private networks. This demonstration shows an open and programmable 5G network in a box solution for private industrial deployments. Our main contribution is prototype implementation of an integrated in a box solution, which is based on an open source software stack and general purpose hardware. Our solution is programmable and it can operate in 5G non-standalone or NSA as well as in 4G LTE modes. We also demonstrate successful end-to-end connectivity in 5G NSA and 4G LTE modes with a commercial off-the-shelf 5G dongle and operation in different sub-6 GHz frequency bands, some of which are dedicated for private networks. We also provide an empirical evaluation of 5G NSA performance based on the open-air interface software stack. So in case you're not familiar, NSA, which is illustrated in the figure above, is a deployment option for 5G which leverages dual connectivity with 4G RAN, and there is a 4G core network as well. The control plane functions are handled by the 4G base station, whereas data traffic is transmitted by the 5G base station. So this is our demonstration setup. We will demonstrate live connectivity and traffic exchange in 5G NSA and 4G LTE modes between the dongle and the network along with live performance evaluation. So this is our 5G network in a box solution. We use software-defined radio platforms as RF frontends for the 5G and 4G base stations, which are also known as G Node B and E Node B respectively. The open-air interface software stack is running on a dedicated mini PC kit. The 4G stack is running on an Intel i7 mini PC with 16 gigabits of RAM, whereas the 5G stack is running on a higher spec i9 mini PC with 32 gigabits of RAM. There is also a clock source for time synchronization between the 4G and 5G SDRs. Next, we start the core network and the two base stations. We also power up the 5G dongle, which you can see here in the front. This dongle is based on the QuickTel RM500Q module that is compatible with 3GPP release 15. Once the dongle is connected to the network, we can proceed with performance evaluation. So next you will see some close-up screen recordings of all the steps between the dongle and the network. Yes, so here is a close-up screen recording. So at the beginning there is no E Node B connected to the core network, as you can see in the top window here. Next we upload the configuration files. On the left hand side you can see the 4G base station and the right side is for the 5G base station. So once the configuration files have been uploaded, the E Node B and the G Node B start transmitting, and the dongle, it also is in the process of connecting to the network at the same time. So here you can see now one of the base stations is connected to the core network now. And here in the top window now you can see that there is a UE which is attached and connected to the network. So now we can proceed with the performance evaluation. We'll start with the latency evaluation in this case. This is the round trip latency between the UE and the core network in the 5G NSA mode. And as you can see from the window on the right hand side, this is on the order of 10 milliseconds. We also do TCP IPF testing to evaluate the throughput performance between the UE and the core network in 5G NSA mode. And as you can see from the window on the left hand side, this is on the order of 22 to 25 Mbps. So next we would like to show you the 4G LTE band operation, and in this case we will be running the configuration file for band 40 on the eNode B, as you can see in this window. So once the configuration file has been uploaded, the eNode B starts transmitting, and the dongle is also in the process of connecting to the network. Yeah, so in this case we start with the latency evaluation, and as you will note from the window on the right, the latency is significantly higher than what we observed in the 5G NSA mode. We also do that TCP IPF testing like before, and in this case the throughput performance that we will be getting is on the order of 3 to 5 Mbps, which is significantly lower compared to the 5G NSA mode. We have also conducted further evaluation in terms of latency and reliability. These results have been reported in the paper, and the details of different frequency bands have been provided as well. For instance, in the 5G NSA mode, we are using band 78 for the 5G base station or the GNode B, and we are using band 7 and band 3 as the anchor bands, or the band which are used by the 4G base station in NSA mode. For 4G LTE operation, we are transmitting in band 3 and band 40, and both of these bands have dedicated spectrum for private networks in the UK. In terms of performance, the mean round trip latency between the UE and the core network in the 5G NSA mode is on the order of 10 milliseconds, whereas the mean round trip latency for 4G LTE mode is 31 milliseconds for band 3 and 47 milliseconds for band 40. The higher latency of band 40 is mainly due to the use of time division duplexing operation. To conclude, we have demonstrated a programmable and open 5G network in a box solution for private networks, along with successful end-to-end connectivity with a Quartz 5G device in both 5G NSA and 4G LTE modes. We have also provided performance evaluation of the 5G and 4G open interface software stack. Our demonstration also highlights the potential of general purpose hardware and open source software for developing white box 5G solutions. Such white box 5G solutions are becoming important as governments worldwide are aiming to diversify 5G supply chains. Thank you very much for your attention, and I hope you enjoyed the demo. Please do get in touch if you have any comments or feedback about this work. Thank you.